All right, so today we'll be talking about the Solow model and the Ramsey model. So this is kind of like the main topics of macroeconomics, like the theory of macroeconomics on a little more of an advanced level that kind of sets you up for a master's in macroeconomics. So it's important to dive into these kind of like micro aspects. In like a moderate level of macro, these would be kind of like covered in one or two lectures, but there's like an entire course just based on those two models. So like now we'll dive into it. So starting with the Solow model. Let me just this here. So starting with the Solow model. So what is the Solow model? This model talks all about rich and poor countries and their growth rate and the theory behind how they grow and why they grow and kind of the competition between it. So we're going to be talking about three different things. The mechanics of we're going to talk about the mechanics of how capital is accumulated in economies and the equation of motion. We'll talk about convergence. This is why some countries grow faster than others. And welfare and the golden rule, which is why are we saving and are we saving the right amount? So starting with the Solow model, let's just, actually I'll leave this here. So, what is it, right? It's the Solow model is an equation of inflow and outflow. So, here we have savings rate. This is K. Minus some parameters. So, what do we have here? I guess. So, the growth in K, in the way capital is accumulated, is a function of, it is the savings rate of the amount of capital we're accumulating, minus, here we have growth in population, technology, and the depreciation rate. So the reason why so this is inflow and this is outflow. So the reason why this is accumulating capital, so it's inflow, and this is outflow because as more people enter the labor force or the workforce, you need more. You need to hire them. They need wages. They need more technology, more machines to work with. So as N grows, your outflow also grows. Here we have this is the efficiency of workers. It's technology, but it's also just how efficient workers are using technology. So the more efficient workers are, the more you have to pay them, and the more outflow there is. And the depreciation is like things like machines breaking down, repair costs. When things depreciate, you have to pay to update them and stuff. So it's this simple. This is the growth of capital. Now, when we set, so for every type of model, there's a steady state. And the steady state is the perfect amount of inflow to outflow. So the steady state here is when inflow is equal to outflow. So to find that, first we have to set the growth of capital to equal 0. So here, there's no more growth. And at this point, we move the outflow to the other side of the equal sign. So we find F equals K over K minus, equals N plus G plus delta. So, or depreciation, yeah. So here what this actually looks like is, so we have a graph here. We have a line and another line. So right here we have N plus G plus delta. Actually, wait, let me, this is important. Where's my, okay, so this is, delete all this. So we have so here we have a graph. We like graphs because they visualize things. So to model S F of K over K and N plus G plus delta, where this is inflow, this is outflow. So this is a linear horizontal line because it's not multiplied by anything that grows over time. These are kind of like constants in the code. So this is simply just that, N plus G plus D. Okay, this is that. Now, this is a little more complicated. And what the Solow model says is that this is a negative line that it actually doesn't matter if it's concave or convex, it has to be a curve. It just doesn't matter what the curve is, as long as it's negative and kind of looks like this. So this is S F K over K. So right here, we have K star. At this point, exactly, we can say that SFK over K equals N plus G plus delta. Anytime before it, it doesn't, and anytime after it doesn't. But what's important to note is that this point is the goal for a country or for like an economy, where their capital, like the inflow of their capital, is the same as the outflow of how much they're spending. So this is basically it. This is the steady state, and this is kind of important to know. Now, the reason why, so I don't know if you've noticed, but there's K. All right, we're back. I don't know. I think I don't know. Okay, so this is uppercase K, this is lowercase k. That's why I keep doing it like this. The difference between this and that is this is capital, and this is capital per effective unit of labor. Now, what does that mean? So, this is probably where I should have started, honestly. But a function of the Solow model is the Cobb-Douglas one, which is Fk over Al. So this is a function of capital and productive labor or effective labor. Now, what I modeled here is a function of capital per unit of effective labor. So this is just capital, this is just effective labor. If we do K over Al and Al over Al, so capital per unit of effective labor, and these just cancel out, so these become nothing. That's the wrong one. These just cancel out. This would be small k, and small k is important because it kind of signifies what we want to talk about more. So then this becomes also lowercase f k. So that's how we get to fk. So back to here. So say an economy is relatively poor. They are here. They have not that much capital. Let's call this K1 for country 1. And then we have country 2 that's a little more, has a little more capital. Both of them have the same target. Their target is K star. That's where their economy is in steady state. And these two countries are kind of fighting to get here. So the thing about the Solow model is kind of the idea that it gives is that developing countries or countries that don't have as much capital grow faster. So here we see country 1, where country 1 has less capital than country 2, grows at a much faster, is in much, like, its growth is much larger than country 2. So this is the growth that we talked about before, where this equaled inflow outflow, 1, 2, and this just stands for growth. So the growth of country 1 is always going to be more than country 2, given its has less capital. But there's an assumption here that we're kind of holding constant that might lead you to a naive point of view. So first, what can we deduct from the idea that a country with less capital grows faster? We can first say, oh, okay, if a country has less capital and grows faster, that means at some point in time, so this is KT, at some point in time, it's going to catch up to K2, and they're both going to end up at this steady state. That's what this graph is telling us, at least. That's not true. That's first what we call absolute convergence. That's absolutely country 1 and country 2 will converge at this point, where they will both reach the same steady state and happy ever after, blah, blah, blah. But that's not the case. A more realistic case is as follows. Okay, so let's assume both countries have the same parameters, meaning the same N plus G plus depreciation, which is already very generous to assume, because that's not true. But let's just start there for simpler reasons. So let's assume country 1, country 2 have different savings rates. So let's just give a random number to the savings rate. We'll say country 1's saving, which remember S is F is times the F of lowercase k over lowercase k, which is saving capital. Let's say it's 40, whatever that is, just to show that it's higher. These numbers are much higher, obviously, in real life. And here the S over K is 20. So S1 is greater than S2. So how that's going to look like here is just two different curves. So 1, 2. These are they could be curves. It's just whatever. Actually, it's important to have it be curves here for what I'm about to do. So, okay. Country 1 has a higher savings rate than country 2. So here, this is S1, this is S2, as it's higher. It's pushed to the right. So that means that country 1's steady state is different from country 2's steady state. country 1 here has a K1 star. What is it? K2 star. So that means country 2 that is poorer has like a steady state, like a goal that is much less than country 1. So let's assume country 2, it's just like, let's assume country, let's assume both of them are below their steady state. So right now they're both here. K0, 1 equals K0, 2. So this is just saying they're both currently at the same place. 1. Okay. All right. So right now they're at the same place. While the poor country has a lower bar than the higher one as to what they want to reach. So what does this mean for K1? Right, so yes, poorer countries grow faster. That's just a given. But not in all cases. And in reality, this is why they're always going to be limited, or it's always much harder to get out of that trap than it is for richer countries. It's that if we look at the difference of slopes here, so because this is a curve that at the steady state, the marginal product, MPK, of capital equals the N plus G plus delta. They have the same exact. I'm not illustrating it right, but if you really zoom in, on a microscopic level, say there's a magnifying glass here, and it just shows that curve to that line. What's really happening is at this point the slope is basically 0. It's still coming in like this, but turning away. So the slope is 0. There's no growth here, basically. So this is just a terrible illustration, whatever. So think of it as a magnet, or say a car is slowing down to the stop sign, because this is the stop sign. It's going to be accelerating from far, but as it approaches the stop sign, it's going to slow down. It has to slow down so it can stop in time. So at this point, so this is currently, this is 2025. This is right now. The growth of country 2, which is the poorer one, is less than the growth of country 1, which is the richer one, which contradicts what we spoke about, because we said poorer countries grow faster. But it's different when they have their own standards, their own ways of accumulating. So here the slope of country 1's growth is more than country 2, although country 2 is poorer. Which is, this is one case of how that can happen. And it makes it where country 2's growth slows down till it hits 0 at its point of stability, while country 1 still has a long way to go. So they still continue to accelerate. Why is it so... It's cleaner than the chalk, because my hands are clean. Okay, so another example of this is, let's say that the countries have they have the same savings, which is fine, but they don't have the same parameters. So the poorer country has a higher growth in their population, which is usually the case. We find in poorer countries, there's more population growth. So that means in n plus g plus delta of country 1, we're assuming country 1, yeah, country 1 has, we'll say country 1 has the higher growth, is greater than n plus g plus delta of country 2. But they have the same savings rate. They're saving the same exact amount of money. So what's this going to look like? So so one curve, not two, just one curve, because they have the same S of capital over K. But because these are different, we have one line here, one line here, where the parameters of 1 versus the outflow of 1 versus the outflow of 2 is more. Is more. So n plus g d of 1, 2. So here they have higher growth rate. The steady state of the country with the higher growth rate, which is assumed to be the poor country, is the poorer country, because its steady state is much less than the one with less growth in population, because they have less outflow, which makes sense. They're accumulating the same capital. They have the same amount of wealth to some degree, like before the outflow. But country 1's outflow is just more. They have more to spend on, they have more labor, more people to give that money, but saving the same amount. So relatively, they're not saving as much as they should be, which puts them at a steady state that's much lower. So, like we say, if they're both here, if they're both right now, currently, at this point, K1, 0, K2, 0, equals, they're both at this point, the richer country would have faster acceleration. Now, this is kind of what's a more realistic look on how countries are, but like the most realistic is another line here showing savings of country 1 being less than country 2. Now the savings of country 1 being less puts its steady state at, so this affects country 1, so it puts its steady state at an even lower mu, at an even lower point than it was before they had less savings, obviously, and K2 doesn't. K2 follows S2, so now the gap is even bigger, and that's kind of the issue that we find with poorer and richer countries. That this gap is just insane. Where here this one could have higher growth rate, but it has goal that's just much less than capital 2, and it just can never get to it unless it has higher S and lower N, lower G, lower delta. So yeah. Now, that basically is the Solow model, but I just want to quickly show the time. I don't know what it's called, the time graph, okay, I'll explain. So, we have where this is ln of C, this is ln of K. Okay, time. So this is the natural log of consumption and the natural log of capital. So, in a point where the capital of a country is, okay, let's just do consumption only. Okay, so let me just get something here. Okay, we'll do this as C over L, consumption over labor. And this is just the normal graph. Okay, so this is optimal consumption. Here we have golden rule. Here's the golden rule. So, at this point in time, at this point in time, where a country is below its steady state, K 0, what does this look like on a log C over L time graph? It looks like this. So right now we're growing like in capital in time. So it's like that. But this is current, 0. So this is a projection of how much we would continue to grow. Right here. This is where we are. Now, getting at the steady state, we decrease consumption to reach the capital goal, basically. So we are consumption has to decrease. So here's consumption over labor, right? Consumption was at this point for now. Now let's have it at this point. So now we're back here. To kind of approach K star, we have to now grow consumption all the way kind of like in infinite time to get to the projection of how K star would look like. So this entire time we're below the optimal level. So the generation that has to go through this, which seems like an infinite generation, is never gonna get the satisfaction it needs, where they're saving and not consuming, and they're trying their hardest to be conservative, but they never actually reach K star, which is not good. Now here's another situation. It's the same thing. This is K0, so current. And then let's say from this point, so again, this is current consumption. So what people might be doing is they sacrifice their own generation for the future generation to have a better way of living. So blah 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 blah, where they start lower, they save a lot and kind of get their consumption to be at a lower level now. So at some point in the current future, whatever, at some point in the current future, they actually reach the steady state where this generation is worse off and the next generation is much better off. So today's consumption, or today's lack of consumption, and today's conservatism pays off in the future once it reaches a certain point, which is like kind of the optimal state, and then we can start eating and saving and kind of like being all better. And that's called the intertemporal trade-off. All right, now we have the Ramsey model. So, in the Solow model, we talked more about, or the whole point was inflow and outflow of an economy, and that consumption is somewhat fixed. Here in the Ramsey model, we try and optimize our consumption as consumers. So we kind of think like, yes, I have, let's say the consumption is corn, but do I want to eat the corn today or do I want to save it for tomorrow? And instead of eating corn, let me go grow some corn in some field to accumulate that wealth for tomorrow. So it has the sense of wealth accumulation, but now we choose how to consume and if we should consume. Like to live you should consume, but we can choose to consume at a very low level to make up for later, or at a very high level now. So that kind of low to high ratio is the impatience parameter. It's kind of like a variable. That variable is important in the Ramsey model, as well as the return and what other variable? Oh yeah, the smoothness parameter. Where these show in this what's called an Euler equation, 1 over smoothness parameter brackets R minus P minus some other parameters, but for simplicity it could just be R minus P. So deciding consumption level depends on the following. Your impatience. So this is how bad do you want to consume now? So if you're patient, you decide, okay, I can consume later. I don't need to consume that much now. But if you're patient, if you're patient, you can consume later. If you're impatient, you want to consume now. So this being high means consume now. The R, the return. So the return on your saving, like the interest rate. This being high tells you I should probably save now, regardless of your patience or impatience. Just says you should probably save more now. This being low says you shouldn't save. If the bank is going to pay you more for saving now, you should probably save now. So the higher the R, the higher you want to save now. And by now, it's like this time period. The smoothness parameter is kind of like the referee, where in this game of like tug and pull or whatever, this controls how much change do I want. This being high means I want no change. This being low means I do want change. And it's in the denominator because the higher it is, the more it's going to depreciate the effect of whatever number is output here because of this number being smaller, showing you don't want that much change. So this being high says no change, or as least as possible. Okay, so I as a consumer, I'm confronted with these, and then I get to decide what I want. So graph this. Would look a little like this, where this is K0, this is C0, K equals 0. So this is my consumption line. This is me right here. This is the amount of capital we have going on. And if you noticed, I drew this off-centered because here that is kind of hidden is the golden rule. So the golden rule is the optimality level we spoke about before, where this is where MPK equals the outflow you have, and there's no growth and there's no nothing, and you kind of just consume equal to how much you should be, rather than here with the slope being steeper, you're consuming more now. So this line is in the Ramsey model can never exceed the golden rule. So the reason why is, another way of showing this is, have it here, I think. Yeah, so the savings for the Ramsey model is A n plus g plus delta, outflow that we had before, delta plus new parameters that I erased, I realized, p plus theta, g, this g is the same g as there. This is the impatience. And what we find out about this is that this is less than 1. Not that it's negative, but it's a fraction. So the golden rule does not account for these new parameters. So look at the golden rule as just A being greater than 1. And with this being less than 1, that tells us A is greater than A plus this, and G plus. So for this reason, we can never exceed the golden rule line. That's just how it is, okay? So, this is capital, this is consumption, if that wasn't mentioned before. And here we introduce a resource constraint, where there's two types of it. There's the continuous one and the discrete one, where the continuous is like more steps of the discrete one. So I'll just start with I'll just show the continuous one. And it looks kind of like this, and I'll explain what it's implying. So, infinity equals 0. E. This fits on the screen. So this is our resource constraint. So our resource constraint compared to our budget constraint, which is this. E R T, so much for saving, plus NG T T DT. K A cost function. W T DT. Okay, so so let me just, here we have the same thing, but if you notice the characters being smaller, which you might not notice because this, I don't know, it doesn't look that clean. This is consumption. This is consumption per AL, as in small c, where this like line over the C shows it's a bigger C. This having no line shows it's a smaller C. And that follows the same thing that we have, the per unit of effective labor. It's the same thing here. So sorry, this isn't the budget constraint. This is the resource constraint when it's over AL, when the like variables are over AL, which is what we're modeling here. This resource constraint is then like it goes in the same equation as a budget constraint, which is here. Okay. So this equation and this equation give us the Lagrangian. And the Lagrangian is basically just the BC plus lambda times the RC. Okay. This is why I need more than a day to study. Okay. The resource constraint is not affected by the lambda. The lambda affects the BC. This is the budget constraint. This is the resource constraint. This is the budget we are constrained to. This is what we have. Okay. Now, that was confusing. Whatever. So, at this point is our Ramsey optimal. This is our golden rule optimal, which we don't touch. So what happens once capital, so this is capital right now. This is consumption right now. So what happens if capital decreases? So actually, like one, whatever, 01. So this is a new time where capital has decreased. Capital decreased because a war happened. So we lost half of our factories. So we lost capital. This is the new area. Immediately, we have to cut consumption. So consumption, one, goes down while capital goes down. This is bad. We don't like this because we lost money, we lost capital, and when we look at our time graph of the latency over time, from here to here, so this also draws kind of a saddle path, which is our recovery, where over time we're going to have to get back to where we were before the war. Here it shows how we were going, us now, how we would have continued to go without the war, and what actually happened, which we dropped, as we saw here, and then had to catch up all the way back to where we were. Now, as we said before, one that looks like this, everyone in this generation is worse off, because this pushes to infinity. This is not a good, like war in this sense, is not at all good. Because we, like for as long as we know, as like a generation, we will just continue to strive to work to the position we once were at. So we're just always less. That's not good. So some other example of this is, let's say we accumulate capital suddenly. So suddenly we have K, right? It can't cross this line. So K, let's just call K2. So it's a new line where we just got a lot of capital, right? At this new constraint. So not only is consumption going to increase, it's actually going to increase a lot to like here, where this is where we are, yeah, C2. So we just got a fresh new batch of capital. So we decided, you know what, let's just really consume. We just got a lot of money, we're very impatient now, I don't like these cuts either. It just happens. Okay. So not only are we gonna consume a lot, we're gonna consume much more than we need to, because we're impatient. Our P is low, our patience parameter is low, R is low, the interest rate on saving, so we don't want to save. There's no point to save now. We might as well consume our money. At least wait until R is high again, then we can save. So we consume a lot more than we should. And this has a different saddle path that takes us from this new equilibrium that we were supposed to be on back to the older equilibrium because of how much we consumed. So how does this look like in a time graph? This is the opposite of the generosity one that we saw before in the Solow, where we're growing at a certain path. This is us now. LNC. This is us now. And then we decide, you know what, let's jump to this new consumption level. So this is C0, this is C2, and this is C1. Yeah, C1. Sorry, yeah, C0. Yeah. Let's just call this 1 and this 0. 0, 1. Okay. This is where we were with this. With here. This is where we are right now. K1, C1, and then we decide, okay, yeah, here. We want to consume a lot because R is down. We're impatient. We want to consume now. So we start from here. We love it. We love the consumption. The normal level should have been like this. We catch up how does this look like? Okay, we're patient, we're impatient, we want to consume a lot. At some point, it has to get back to an equilibrium, but it doesn't get back to today's equilibrium. It gets back to the equilibrium that used to be there. So this is C2, C1 is here, like this. Okay, and then, all right, okay. And then the line of consumption goes like this, where this would be the saddle path, approaching the past equilibrium. And what happened here is all the new generation is now worse off, because they could have had this increase because of the like point that we had, but they didn't, because we consumed way more than we needed to now. So right now we're better off. And that is the result of having impatience being high, change not caring how much we change, and our interest rate being low now. Where being high would have made us a bit more conservative. And then we said, you know what, let's just let the other generation deal with the circumstances, with the bad circumstances, and that's exactly what happened. Yeah, there. So anything above here is good. Anything here is good. Anything after is bad, because we would have just continued to go up. So yeah, that's pretty much it.